Hello, everyone. Good morning. We're going to get started here with the first session. And so the first talk of the first session is Brett Slatkin with how to be more effective with functions. Let's all thank him. Introduce.
Great. OK. Can I get on the screen here somewhere? My presentation. OK, my name is Brett Slatkin. I'm a software engineer at Google. It's my day job. I also recently wrote a book called Effective Python. I like my slides over there. There they are. Cool. So the talk today is about how to be more effective with functions. So I realize it's the first session of the first day. I'm still drinking my coffee. I'm still waking up. So I'm trying to set expectations for this talk. Really quickly, show of hands, who knows what this means? So who's ever used an expression like this in a program? Iter-foo is iter-foo. That's great. OK, good. Yes. Not that many people, probably 10 people. So my goal by the end of this talk is to tell you what this means. This is supposed to be a novice talk. This is the book. This is where you can get the slides and code. There's a link at the top if you go to effectivepython.com. It's supposed to be a novice talk, but it's more like every slide is novice, but put together it's really confusing, perhaps. So please follow along. This is the agenda. That's a lot of words, so I'm going to just go as I go. This is the code, though, that we're going to be talking about today. So first, we're going to talk about star args. Then we're going to talk about keyword args. Then we're going to talk about keyword-only arguments. Then we're going to talk about generators and yielding. And finally, we're going to explain why iter-foo is actually a useful thing to do. Can everyone hear me OK? Am I doing good? OK, and then can people see the slides all right in the back? Can I get a thumbs up? Cool. All right, so let's get going. First thing is star args. So I think that you should reduce the visual noise in your programs by using variable position arguments. And so let me tell you what that means and why. So here's a function. It's a log function. It takes a message, like a string message, and a list of values that you want to print out along with the message. If there are no values, then it just prints the log message to the terminal. If there are values in the list, then it stringifies them, and it joins them together using a comma, and then prints it out. So pretty simple. If you want to use it, here's how you use the log function. You say, hey, my numbers are 1 and 2. And if you have no numbers to print, then you pass an empty list, and it prints nothing at the bottom. So those are our two cases. So at the top here is the code. At the bottom is the output that you expect from the program. Now, this is kind of ugly because the 1 and 2 has these brackets around it, extra brackets you don't really need. When you have no values to pass, you still have to put an empty list there. It's really just noisy. And so you can fix this in Python with special syntax for variable position arguments. And the thing that's really nice about it is you take this function that operated on a sequence before, and you just add a star to it. That's it, right there. Just put in that little star. And what that does is it makes it so your function can work like this. So where this was the way before, you had to explicitly pass a list. Now you can only pass the parameters when you want to. So this is the old usage, and this is the new usage. So this is really nice because it reduces the noise of the function, makes it a lot easier to read, makes it so you don't have to pass an empty list, which is just really unnecessary. One of the things, though, is that maybe you already had a list and you wanted to pass a list in. And you can still do that in Python. You probably may have seen this before. So if you have a list, you can use star on the list, the star operator on the list when you make the function call. And that will have the effect of calling it with the parameters in line like this. So it's the same outcome. And you'll see that what it prints is the same in both cases. The only problem with that is if you use a generator in this case, the program is going to crash. It might even crash your computer, depending on what you're doing. So this is a generator that just yields every number, starting at 0. And if you use the star operator on a generator, what Python's going to do under the covers is it's actually going to iterate through that sequence and turn it into a tuple. And that tuple for all integers becomes infinitely large. And so depending on what your computer is and your ulimit, like on Linux, it'll probably crash with a memory error. On a Mac, it might just fill your hard drive and swap space until your battery drains or something like that. So this is beware. And so the real conclusion here is that variable position arguments are really good for removing noise. It's to make your code more readable. It's not just saying like, oh, all of my APIs should work on a sequence, so I'll just have it work on star args. You really should only use it for the convenience of the programmer, for the readability of your code. It's not there to be an N API versus a single call API. So that's the first one, trying to get harder and harder as they go. Next one is providing optional behavior with keyword arguments. So I think you should do this. And there's a keyword argument right there. Motivating example here. I thought it needs to be more connected to the real world. So imagine that you are trying to calculate the flow rate. This is my high quality illustration. Maybe this is cream cheese for bagels or something like that. Whatever they do in this town. I have a scale, I have a vat sitting on a scale, I have a clock, and the idea is that I'm calculating how much material has flown into the vat at some period, okay? And the idea is I can calculate the rate of flow by taking different weights at different times and then calculating the difference. It's also known as division. So this is flow rate. So this is our function. And so this is great. You can put it to work. So if I have half a kilogram going into a vat in 3 seconds, that's going to be 167 grams per second, 0.167 kilograms per second. And that's great. And so this works as you expect with division in Python 3 because that's not integer division, but that's a separate story. But now let's say that you wanted to support some alternative units. Like I'm from America, so I use imperial units for some reason. And so I want to add to this the ability to do pounds, and maybe I want to calculate flow rates over longer periods of time. So to do that, I can add these two parameters, the period and the units per kilogram, conversion rates. And this is just a simple unit conversion function. I just added in some extra multipliers. So I can put this to work now using some extra parameters. Here I have keywords in there to make it really clear what I'm trying to do. And you'll see, so now I pass in 3,600 seconds for an hour and 2.2 pounds per kilogram. And I get out the same numbers as before are 1,320 pounds per hour is the flow rate in another set of units. So this works really well, but the problem is that you still have to pass the units even if you don't need them. So I've added these parameters, but they're not optional. And if you leave them out, Python will get mad at you and say, hey, like you need to pass the period and the units per kilogram. So this is noisy, it's redundant, it just doesn't make sense to have to do this every time. So that's where default argument values come in. So where the function was like this before, all we have to do is add the default values to the function signature with 1 and 1, and you get this new behavior, new capability in the function. And what's so cool about this is that all existing function calls don't have to change. So if you're adding functionality to an existing function, default optional arguments or default values for optional arguments let you add functionality over time without breaking the callers. So existing function calls on top will just keep thinking it's kilograms per second. New functions that know about the new functionality, or new calls to the function that know about the functionality, can pass in the new parameters and get the new capabilities of the function. So this is a really nice way to extend things. So again, keyword arguments let you omit arguments that you don't need. New seeds can access new functionality, and then you don't have to update, you don't have to refactor your code to add functionality, which is really nice. Okay. Am I going too fast? Too slow? I'm trying to go fast because I want, okay, I got 1 thumbs up, that means I'm going too fast. Slow down. So I want to talk about one of the problems with this approach of passing keyword arguments. And the problem is that you're not forced to be clear. So I think that you should enforce clarity with keyword-only arguments. Keyword-only arguments make it so that you have to be specific about default arguments. So here's what I'm talking about. Let's say that we wanted to calculate ounces per second or per minute going into the vat. Which one of these is right? Well, you know, is it so 60 seconds is a minute, 35.274 is a conversion rate for ounces to kilograms. But the question is, was it did period come first? Did units per kilogram come first? I actually don't even remember, and I wrote the code. It's not clear. So when you have two parameters of the same type, you've really got a problem, because when you look at the call site, it's not obvious to you what each of the parameters refers to. And you'll see this all over Python code. This is a really bad practice. It's kind of like it's an anti-pattern. So luckily, Python 3, and we'll talk about Python 2 in a second, lets you solve this very easily. You take this function definition from before, exactly as it was, and all you do is you add a star to it, right there. And by doing that, everything that comes after that star is required to be passed as a keyword. That's it. That's all it takes. And so now, when we go to this negative or anti-pattern example from before, you'll see that Python will actually complain at us and say, hey, I can't take those arguments positionally. I have to take them as keywords. So that's the benefit here, is that it forces the caller to change their code to pass in keyword arguments specified using the actual parameter name. So this is the best practice. You should always pass optional keyword arguments with the name. That's just generally good style. But especially if you have two parameters of the same type, you really should do keyword-only arguments so that it's never ambiguous what is being used for what. Especially if your function is taking like Boolean values like true and false, you really need to do that, or else it makes no sense what's happening. Really quickly, if you have a log function like the one before, and you want to extend this function, this is especially problematic. So let's say that I want to take this log function and add a sequence number to it. So the sequence number could say like what order the messages came in for a log or something like that. So here I've added a sequence parameter. I've added it to the first print statement, so it gets printed first. I've added it to the second print statement, so it precedes the message that's been formatted. Now the problem with adding it to the beginning is it's going to break existing callers. So new callers that know what's going on, they can put a sequence number in the first position, and the log function will work as expected. You see down here, it's 1:favorite 733, and that works. But all old usage is now broken. And because Python uses %s in nice ways, like this %s, like the string format in out right there, and the %s in that print statement, when you do that in Python, it'll convert anything you throw in there correctly. And so, it'll hide errors that you never meant to put in there. Maybe you didn't mean to have a string in there. Maybe you accidentally passed an object or an integer or something like that. Python won't explode when it does this. And so you get this really wacky behavior where at the bottom here, favorites : is the sequence number, which is definitely not what we wanted. Like that was not the goal. So we've broken the code, and you will not find it. Like this is a total anti-pattern. If you're going to use variable position arguments, never do this because you will mess it up. You will not find that one caller. Something wrong will happen. Luckily, you can solve this problem, and all you have to do is use a keyword-only argument. This is the syntax in Python 3. In Python 2, it's slightly different, but I have it in the appendix if you're curious. But all you have to do is just say, OK, I also want to get the sequence value. And what I'm doing here is, if the sequence value isn't supplied, then I just pick one. So time. I just grab the current time, and I'll set the sequence value to the current time. And the rest of the function's the same. And so now when I call it, new usage works correctly by passing a sequence number of 1. Old usage that doesn't know what's going on will continue working, and it'll take on the default value for that new keyword argument. So this is a really nice way to extend any function that takes variable arguments without breaking existing callers. So one more time, you want to use keyword-only arguments to require clarity. It's really important if you have things of the same type, arguments of the same type. This is really the best way to extend star args. And you can actually do all of this in Python 2. The syntax is slightly different. It's not as pretty, but you can achieve the same outcome. So you can use it there too very easily. OK. How am I doing? I'm doing OK. Everybody still with me? People waking up a little bit? OK, doing OK. All right, so now it's going to get a little bit harder. So let's talk about another part of functions, returning values, either lists or generators. So I have, I think that you should consider generators instead of returning lists. I think Python programmers often just return lists because it's easy. And I'd like us to have kind of a cultural change where we instead of saying why use a generator, it's like why are you using a list? You know, that should be the default way that we implement things. And I'm going to try to explain why. So let's say I have a file of some data. This is a population of people in the province of Quebec, and I got this from Wikipedia, so it might be wrong. So I'm going to load this data file. It's tab-separated data. Here's a function to do it. Load cities list. It takes the path to the file on disk. It creates a list of output. It's going to be the city names and the number of people who live there. I'm going to open up the file as a handle. I'm going to go through every line in the handle. I'm going to split every line by the tab into the name of the city and then how many people live in the city. Then I'm going to append that tuple to the output list. And then I'm going to return the output list back to the caller. And you can put this to work. You can see that it works. I have this population tab-separated file that you can run it on. And you'll see that Montreal is the largest, followed by Quebec City, and so on. And that works great. The problem is that you might run out of memory if you do this in other cases. So if you have, say, this is great for Quebec, but let's say you want to load a list of cities in the entire world, something like that, giant file or other data files besides these ones, eventually there'll be so much data in this list that you'll run out of memory and crash, your program won't work. So generators are a great solution to this. It's really easy to implement them. Here's the list version, and here's the generator version. So what's really interesting is it's actually less code, and it's easier to read. So some people think, oh, generators, those are too complicated for me, I shouldn't use them. But really, it's actually easier. And the big differences are you don't need the out list anymore. You don't have to return anything. And then when you append the tuple, you don't need this extra parenthesis, which is kind of hard to read. So just everything gets a lot more legible in this version. And you'll see that it works as before. I have to call next on it because it's a generator or an iterator instead of a list, so you don't have everything right there. But the benefits are there's less noise. There's no out equals or return out or parenthesis. The file can now be of any size. All of the memory problems that we had are gone. And this question, so again, the question should be, why, when you're writing a function, why are you returning a list? Why are you not defining a generator? You should just always be defining a generator, unless you have some really good reason. Okay. This is the thing that's going to take a while. So, trying to get you warmed up for this one. Okay. So, I think that one of the most important things for you to do when you're writing functions is to be defensive when you're iterating over arguments. And this is a subtlety. I'm curious at the end how many people have been burned by this. I've been burned by this so many times, and I feel like it's like a badge of honor that once you've crossed the threshold of being burned by this, you realize this. And iter-foo is the actual way out of this problem, and I'm going to explain why. So let's take that population data that we had before. So we've got the population breakdown by percentage that I'm trying to calculate here. So it's great to know that 1.6 million people live in Montreal and some number live in Quebec City, but I'd really like to know what percentage that is of the total number of people who live in all of Quebec. So here's a function to calculate that. You pass in the list from before or the generator from before. First, I calculate the total number of people who live in Quebec. So I take the whole file, I go over all the lines, I take the count from each line, and I sum it up. So that total equals sum, that's what that line does. Okay? So that gets me 6.5 million people or whatever the total population is. Then the for loop does this a second time. It goes through the whole population a second time. It takes each population for each city. It divides it by the total. That's the percentage that city has of the total population. And then it yields that city name and then the percentage of that city is of the total population. So now I can run this. Here it is. You can see that Montreal is 25% of the population. Quebec City is about 8%. And I have to run next on the return value of normalized because it's a generator. So it's returning an iterator. And so instead of getting a big list out, I have to go through them one at a time. And so this works properly, and that's great. Now you'd say, well, hey, you shouldn't be using this list function. I thought we just talked about that. Shouldn't you be using a generator instead, following your own advice? Surely I should be. That's right. So let me do that. And then what happens is the function doesn't work. So I was sitting here telling you that you should do this, and clearly you should not do this because it broke. And what happened was we passed in the generator, and we got out a stop iteration exception, which is just nonsensical. It doesn't make any sense. What's actually happening is we're getting out an empty list, basically. There's nothing yielded from the generator. And the question is, how can this happen? How is it possible? Because we know load city's generator works, and we know normalized works. So there's some combination of normalized and the generator that's not working. And here's the reason. And this is the gotcha that you'll get bitten by at some point. We iterate over the population argument 2 times. And when you first read this function, you don't actually realize that that's what's happening, but it's a big problem. So the first time we iterate over it is for the sum. So we go through the whole file, calculate, figure out the total population of the entire province, and then sum it up into the total. Then we iterate over the file again, and we go through each city and figure out its contribution to the total. So you have to do this. It's just the nature of the problem. You have to sum everything up, and then you have to divide. There's a whole set of problems that are of this kind, and they all suffer from this. And the reason this doesn't work is because if the pop argument is an iterator, then sum is going to just iterate all the way through it until it's exhausted. So sum will just keep going next, until there's nothing left, and it's like, cool, I'm done. Here's your total. And then the for loop says, okay, now I'm going to go through the same iterator, and the iterator says, I have nothing left. Stop iteration. I'm done. The problem is that Python doesn't know the difference between those 2 circumstances. I don't know if it's a design flaw in Python. You could argue either way. But the point is that Python doesn't know the difference between an iterator that's been exhausted, been fully run, and an iterator that had nothing in it in the first place. That's the fundamental problem here. Python can't tell the difference. So let's talk about the Iterator Protocol really quickly. How do you detect an iterator? What does an iterator really do? So iterators let you go through a sequence one step at a time. What's interesting about them is there's this thing called the Iterator Protocol that Python has that lets you inspect something and determine whether or not it's an iterator. And what the protocol says is when you iterate over a list, you get an object. So when you call the iter built-in function on a list, you get an iterator. When you call the iter built-in function on an iterator, it returns itself. And so what you see here is that so C and B are the same thing. So B is iterating over the list, C is iterating over the iterator, and B is C. They're the same object. You have the same address in memory. I printed them out down here, and then the actual return value is true. And so that's just the definition of iterators in Python. But that's so that's a way to detect what's going on, and that kind of hints at the solution to this problem also. Similarly, how do you detect if an iterator is not the same, or it's a container? And so you'll notice here B and C, the only difference between these is on line B, I'm iterating over A. On line C now, I'm iterating over both A a second time, right? And so when I iterate over a sequence twice, I get 2 different objects. At the bottom, I get false, and the memory addresses are different. So the big difference here is if you iterate over a sequence twice, you get different iterators. If you iterate over, that's this one. If you iterate over an iterator, you get the same iterator again. And that's the problem. So, and that's what's causing this behavior where we get nothing back. So to wrap it up, the simplest thing you can do to solve this is to just use a list. That's what everyone's been doing. If you want to do this the right way, my suggestion for you is to take this generator function and go a little bit further. So here's the generator function from before. I just expanded it out so you can see everything that's in it. And all you have to do is turn this into what's called an iterable container. And it's a really small class, and this is all it is. This is the actual difference. The meat of the program is the same. It's just a little bit of boilerplate around it that tells Python what you meant, what you're actually trying to do. So this is an object. You hand it the path of the file that you want to iterate over, and you find this special method called iter. So double under iter. And now Python will understand how to treat this like a container, like a list or a dictionary or set, like the standard other containers that are in Python. So again, none of the functionality is different. It's just the packaging of it. And if you use that construction of an iterable container instead of a generator, suddenly everything works. So the code hasn't even changed. Like the meat of the function is the same, but now suddenly it works correctly. If I create the load cities object at the top and I pass it into the normalized function, then I get Montreal's 25%, Quebec's 8%, and so on. So why does this work where the other one didn't work? And the answer is, when you call pop here, what that actually tells Python to do is iter pop. So iter pop then in turn calls pop.iter. And that's the solution. Because when you call pop.iter, you get a new iterator for each call. The old way, you're just using the same iterator, so Python's just going to go through it. But when you define a container, an iterable container, Python knows to do this magic where it's like, oh, pop, I know I'm going to iterate over pop, cool. I'm going to iter over pop, okay. That actually means I'm going to call this function instead. And that solves the problem. Yeah, so that's the real solution. The last thing I'll say on this is the final end of the riddle. So you can determine whether or not you're going to get bit by this if you run this code. So here's the not defensive one, and here's the defensive one. So when you get an argument into your function, you can test that argument and you say, is iter pop the same as iter pop? This is that silly expression from before. If pop is an iterator, it returns the same thing to both of these calls. So iter pop is iter pop will return the same exact object. This will be true, and you know this is a big problem. And so you can just bail out and say type error, like you cannot call this function with such an iterator. If it's a container, like a list, a set, or that nice load cities iter method that we under iter that we defined, this will work properly, and everything will be great. And so you can see here, if I call normalized defensive with that generator from before, instead of getting an empty list, I actually detect the situation. I raise a type error. And so I've now protected myself. So I've made a defensive function. And then if I pass in load cities, everything works as expected. So beware of multiple iterations over the same argument. That's just when you're defining a function and using generators, this is a huge gotcha. It's going to hurt. You should define and use containers to avoid the problem. You can use iter as iter to make sure that you're doing the right thing in a duck type kind of way. And just in general, you should know the Iterator Protocol and look it up, make sure you have it all set. Cool, I'm almost out of time, and I wanted to have time for questions, but I don't think it's going to happen. The last thing I'm going to say is all of this stuff and much more is in the book. If you're interested, I convinced them to give us 50% off for the ebook today, so it's like $16. If you go to informant.com/deals, the slides encoded there, and I'm at Hacksaw or onebigfluke.com. So if you like that and you want even more, that's just the beginning part of the kind of things I talk about, and that's all. So thanks for coming.
So yeah, well, thank you very much, Brett.
Yeah.
Unfortunately, you're right.
Yeah.
There's no time for questions,
Okay,
but
I'll be down here if you need to ask a question.
exactly what he just said.